Hi, welcome to Operations Analytics. I am Dr. James Rowe from Roller College of Business at Rowan University. The topic of this lecture is queuing theory modeling. The study of waiting lines, called queuing theory, is one of the oldest and most widely used quantitative analysis techniques. Waiting lines are an everyday occurrence affecting people shopping for groceries, buying gasoline, making a bank deposit, or waiting on the telephone for the first available customer service agent to answer. Another term for waiting line is queue, and it may also take the form of machines waiting to be repaired, trucks in line to be uploaded, or airplanes lined up on a runway waiting for permission to take off. In this lecture, we will discuss this important topic together and learn how to understand waiting lines and expect the average wait time and the number of people who would be in the line. Let us review the structure of this course. We have learned linear programming and covered prescriptive analytics. And by covering this topic, we will conclude predictive analytics session. Waiting line is to predict how many customers or demand will be on the line and how to prepare for them in advance. This model also can tell us what the current capacity for servicing the demand is. After finishing this topic, we will move on to Module 6 and 7, which pertain to descriptive analytics. Learning objectives are threefold. First, describe the basic queuing system configurations, the calling population, the queuing itself, and the service facility. Second, analyze waiting lines for single-channel models. Third, understand waiting lines for multi-channel models. So in this lecture, we'll review the basic queuing system configurations first, and then waiting lines for single-channel models, and we will expand that into waiting lines for multi-channel models and other examples. Before jumping into queuing theory, let us think about why queuing theory is important for us to study. The first is the wasted time. If you look at this picture, people are waiting outside to get the service or product. Customers spend their precious time in waiting for something. Whether it be COVID-19 vaccine shot or seeing a doctor, customers are spending much time for scheduling, waiting, and having the service done. If we add the time that customers are waiting together, it might amount to thousands of years. We don't know to we don't want to steal the time from the customers. The second reason is related to cost. There is a business reason for waiting time. It results in dissatisfaction and bad impression toward the service. Look at this graph. Cost of providing service increases as a business adds more staff, line, or machine to the service. In addition, cost of waiting time decreases when service level increases, right? So service level increases, so the cost of waiting time decreases. A business needs to find an effective point that optimizes the cost and satisfaction of the customers. Doing so, a business can run their service effectively. Although queuing theory has been around for a long time, this topic is still relevant and will be relevant in the future as well. The first topic that we want to cover is characteristics of queuing system. And here I want to talk about the basic knowledge, fundamental knowledge of queuing system. The three basic components of a queuing process are arrivals, service facilities, and the actual waiting line. Population of arrival characteristic is an important consideration. Population sizes are considered to be either unlimited or limited. When the number of customers are or arrivals on hand at any given moment is just a small portion of potential arrivals, the calling population is considered unlimited. A good example is cars arriving at a highway toll booth, shoppers arriving at a supermarket, and students arriving to register for classes at a large university. Think about cars, constantly crossing Benjamin Franklin Bridge um, and paying for tolls. Most queuing models assumes such an infinite calling population. But there are also examples of limited population. For example, a nurse might cover 10 rooms per shift. A certain small airport might process 50 airplanes per day. Or an engineer has to take care of 5 machines in the factory. In these cases, the arrival characteristics is finite. At that time, we need to use a different method to solve the problem. We also assume that the arrival characteristics of customers are usually random. By this assumption, we can say that the distribution of the arrival characteristics follow Poisson distribution. When the demand is known, we should use a different type of distribution. The second portion of queuing system is queue characteristics. The length of a line can be either limited or unlimited. A queue is said to have a limited queue length when it cannot, by the law of physical restrictions, increase to an infinite length. This may be the case in a small restaurant that has only 10 tables and can serve no more than 50 diners at an event. However, analytic queuing models are treated under an assumption of unlimited queue length in this lecture. Another characteristic of queue characteristics is whether we are using FIFO or emergency priority. This refers to the rule by which customers in the line are to receive service. Most systems use a queue discipline known as the first in, first out rule or FIFO rule. However, sometimes there are exceptions to this rule. For example, in a hospital, emergency room, or on express checkout line at a supermarket, various assigned priorities may preempt FIFO rule. Patients who are critically injured will move ahead in treatment priority over patients with broken fingers or noses. Shoppers with fewer than 10 items may be allowed to enter the express checkout queue but are then treated as first come and first served basis. The third part of any queuing system is the service facility. It is important to examine two basic properties of service facility characteristics. The first is the configuration of the service system, and the second is the pattern of service times. A single channel system with one server is typified by the drive-in bank that has only one open teller or by the type of drive-through fast food restaurant that has become so popular in the United States. As you can see, there's only one line and one service facility. If, on the other hand, the bank had several tellers on duty and each customer waited in one common line for the first available teller, we would have a multi-channel system at work. Many banks today are multi-channel service systems, as are most large barbershops and many airline ticket counters. As you can see, there is one line, however, there are multi-channels. So I should have shown you this. So one line and 3 channels, and these are multi-channel model. The third one is a single phase system is in which the customer receives service from only one station and then exit the system. A fast food restaurant in which the person who takes your order also brings you the food and takes your money is a single phase system. So is driver's license agency in which the person taking your application also grades your test and collects the license fee. So in that case, single phase and single line model is right here. But if the restaurant requires you to place your order at one station and pay at a second and pick up the food at the third service line, then it's a two-phased or multi-phase system. So here is another case. Usually for McDonald's, you come up there and then pay and then move on and then receive the order and then move on and then receive the drink. Then that's a three-phase model and single line three-phase model. In this case, you have a very many different types of patterns, phases. So here's a one line, but multi-channel and the multi-phase model. Service patterns are like arrival patterns in that they can be either constant or random. If service time is constant, it takes the same amount of time to take care of each customer. This is the case in a machine-performed service operation, such as an automatic car wash. More often, service times are randomly distributed. In many cases, it can be assumed that random service times are described by the negative exponential probability distribution. So here is a exponential smoothing model, and here's the function f of x equals mu e to the power of negative mu times x probability. And it tends to decrease exponentially like this. The exponential distribution is important to the process of building mathematical queuing models because many of the models' theoretical underpinning are based on the assumption of Poisson arrivals and exponential services. Before they are applied, the quantitative analysis can and should observe, collect, and plot service time data to determine if they fit the exponential distribution. So one has to check whether the distributions are following either Poisson or exponential model. Here is the weighting models that we are going to be covering. Kendall's notation is very famous for us to understand. So here is MM1 and infinite model, and these are standing for something. So MM1 means Poisson distribution for number of occurrences. That's the first line. Arrival rate is lambda per hour Poisson distribution. Then you use M. If that is not the case, there's a constant rate, then you could use D here. Or you could use Z, general distribution with mean and variance known, then you can use it here too. And the second one is service rate. So this is arriving rate and service rate, whether the service or the business is taking care of or processing the demand or customers. That's what this second M stands for. And this one can follow exponential distribution or constant rate or general distribution. And in this case, we are using typically exponential distribution, then you can use M. And the third one is how many servers you have. If you have only one line, that's one. But if you have two lines or three lines, more than that, then you could have two or three or four and so forth. And queue length, is it infinite or is it finite that you can specify here? And population, it could be finite or infinite population that can be specified there too. So as you can see, here are examples. MM1 means Poisson distribution and exponential distribution and one line, or MD3 would be Poisson distribution for arrival rate, but for service rate, it is following constant rate, and there are three lines, so three lines, and that's what it means. MG4 is similarly, there are four lines, and the distribution for the service rate is general distribution.